So where we left off last class was on the MM1 queue. That's a queue where there's an infinitely long queue, and the arrivals, the distribution of time between each arrival is totally random. It's Markovian. And the distribution between service times is also totally random. So what we want to do is we want to figure out when you arrive at an MM1 queue, how many customers do you expect to see in front of you? And if we knew the arrival rate, lambda, and we knew the service rate, mu, and we knew that the queue was MM1, our goal is to try to figure out how many customers do we expect to see in front of us at the queue. So the way we're going to analyze this, we're going to use what's well known as the birth-death analysis or birth-death processes. If you want to Google it, you can Google birth-death, and you'll see a lot of write-ups on the internet on this. And the idea is basically this: we want to ask ourselves, we want to do a probability expectation. We want to ask ourselves, what is the probability we are in state 0? State 0 means the number of processes in our queue is 0. Nobody's in the queue, nobody's being served. State 1 means we have one customer in the system, one in the server, nobody's in the queue. State 2 would be we have 2 customers in the system, one in the server, one in the queue, total of 2. And then state 3, 4, and it goes off to infinity. So we want to calculate what percentage of the time are we in state 0, what percentage of the time are we in state 1, 2, all the way up to infinity, and then calculate what is an expected value for what's in the queue when we arrive. So the idea behind birth-death analysis is kind of, I like to think of it like you are in a building and there's an elevator that starts at the lobby. Let's say state 0 is the lobby, and then there's a first floor, a second floor, a third floor, and it goes up to the end of the building. And at the beginning of a day, the elevator starts at the lobby. As time goes on, the elevator goes up and down and up and down. So maybe somebody wants to go to the third floor, so the elevator goes to the first, second, third floor, lets the person out, goes back to the first floor, back to the lobby. Then maybe it goes up to the second floor, picks somebody up, and then goes back to the first floor. Then maybe it goes up to the 8th floor, and then it goes back to the first floor. And this goes on all day long. So suppose I told you that over the course of a day, the elevator went from the lobby to the first floor 5,000 times. It went from the lobby to the first floor 5,000 times. How many times during that same day did it go from the first floor back to the lobby? Yeah, from 5,000, right? Because every time it went from 0 to 1, it must have done a corresponding 1 back to 0. As the floors get higher, maybe there's less traffic up there. If over the course of the day I told you we went from floor 2 to floor 3, it doesn't mean we have to stop at that floor. We just went from 2 to 3. Maybe we went from 2 on our way to 5, but we're going from 2 to 3 on the way. So if I told you over the course of a day it went from 2 to 3, 3,000 times, how many times did the elevator go from 3 to 2 that same day? That would be 3,000 times. So we're going to look at this and say to ourselves, every time a customer arrives, and we know the arrival rate to the whole system, the whole queuing system, the arrival rate is lambda. In a queuing system, not in an elevator system. Every time a customer arrives, we go from some state, let's say state 2, to its next highest state. So maybe an arrival comes, we go from 2 to 3. Or an arrival comes, we go from 8 to 9. Every time an arrival comes, we go from some state to its very next highest state. And in an MM1 queue, as long as we are in a state of 1 or higher, if we are in a state and a service is completed, we go from some state to the next lowest state. So if a service is completed, we might go from 2 to 1, or we might go from 8 to 7, every time a service is completed. So if we asked ourselves, at what rate, how many times per day or per second At what rate do we go from state 2 to state 3? That's not lambda. Lambda is the rate at which we go from some state to the very next state. I'm asking specifically, at what rate do we go from state 2 to state 3? It would be the percentage of time that we are in state 2, right, over the course of a day. The percentage of time that we are in state 2 is, let's say that's 10% of the time. Well, then of all the customers who arrive, because it's an MN1 queue, of all the customers who arrive, 10% of the time we go from 2 to 3. From 2 to 3. If 100% of the time we go from some state to the next highest one, and we happen to be sitting in state 2, let's say 10% of the time, then 10% of those arrivals will take us from 2 to 3. And at what rate do we go from state 3 back to state 2, which should equal the rate at which we go from 2 to 3 should equal 3 to 2. It's the percentage of time that we are in state 3, and we have a service completion. And we know the rate at which we have service completions, we go back to state 2. So we're going to make an observation that says, well, here's just a recap of what I said before. You had an elevator that went from, floor 2 to floor 3, 5,000 times a day. How many times does it go from floor 3 to floor 2? Also 5,000, or maybe 499 if the elevator got stuck on the top floor. So we're making the observation that the percentage of time we were in any state, state I plus 1, and we have a death, our population shrinks by 1. Someone gets served, that equals the probability we're in the next lowest state and someone arrived to our system and we went up to the next state. So the percentage of time we're in state 8 and someone leaves our system is equal to the percentage of time we're in state 7 and someone joins our system. The number of times we went from 7 to 8 equals the rate at which we go from 8 to 7. Okay. Now we know, out of all the percentages of time, the only one we really know is the state of 0, the probability we are in state 0. We know that rho, which is lambda over mu, is the percentage of time the server is in use. The percentage of time that we are in state 0, nobody's in our system, is 1 minus rho. This would be the percentage of time that the server is idle, doing nothing. So 1 minus rho is the percentage of time we are in state 0. That's really the only state we know. But now we're going to use this birth-death equation to say, well, the percentage of time we're in state 0 and a customer arrives, that's really the rate at which we go from state 0 to state 1. That we know is equal to, by birth-death analysis, the percentage of time we're in state 1 and a customer leaves our system. We have a death. Someone leaves our system. So we know this is true, and we actually know lambda and mu, and we know the percentage of time we're in state 0, which is this. So we can figure out what is the percentage of time we're in state 1. It's just lambda over mu, a fraction of the time we're in state 0. This birth-death analysis for an MM1 queue is true for every state. Any state is equal to lambda over mu times the percentage of time we're in the previous state. That's true for all n off to infinity. So if you wanted to gather all the lambda over mu's together, because they're just going to keep building up, we could say the probability of being in any state is lambda over mu raised to the n times the percentage of time we're in state 0. And if we summed up all the probabilities of being in all the states all the way off to infinity, it would all add up to 100% or 1. So that implies that the sum of all of these adds up to 1. Okay. So you may recall from calculus. Have all you guys taken calculus? Okay. You don't know? Okay. So maybe you know this is true, maybe you don't know this is true, and I can even show you on an Excel spreadsheet if you don't know calculus. But the summation from I equals 0 to infinity of x raised to the I, as long as x is between 0 and 1, if x was greater than 1, this would go off to infinity, obviously. But if x is between 0 and 1, as you raise it to a bigger number, it gets smaller and smaller, and this would sum to a finite number. So it turns out that this summation, the reason we're talking about summations now is we want to know what is the expected number of customers in our system, and it looks like our probability is to sum off to infinity. We'd like to have it be a finite number. So the sum from 0 to infinity of x raised to the I, when x is between 0 and 1, is actually going to be equal to this fraction, 1 over 1 minus x. And in our case, since lambda needs to be less than mu, otherwise our mm1 would grow off to infinity in size, then lambda over mu, which is another way of saying rho, is between 0 and 1. So if we were to sum up lambda over mu raised to the I times the probability we're in state 0, if we were to sum this all up, it would all add up to 1. So if this statement is true, this statement is true. And we know this is true. We know that the percentage of time we were in state 0 divided by 1 minus is 1 minus rho, and if you divide it by 1 minus rho, that would equal 100%. So even if you didn't know calculus, if you didn't know this was true from calculus, from queuing theory, you can show that this is true. Because you know this must equal this. Okay. Okay, now, to figure out the expected value of a random event, maybe in your probability class, if you've taken probability class, you might have had a question like, if you were to roll a dice, what would be the expected value coming out of the dice? So the way you figure out the expected value is you sum up over all the possible outcomes. And a dice, you roll a dice, there's only 6 possible outcomes, 1, 2, 3, 4, 5, and 6. Each one, if there's nothing wrong with the dice, each one has a 1/6 chance of happening. So you say, okay, the outcome is 1, and the probability of it happening is 1/6. The second outcome is 2, and the probability of that happening is 1/6. And then 3 and 1/6 and 4 and 1/6. So you say 1 times a 6 plus 2 times a 6 plus 3 times a 6 plus 4 times a 6 plus 5 times a 6 and plus 6 times a 6. You add it all up, you get 21/6, which is 3.5. So the expected value when you roll a dice is 3.5. Yeah, now obviously you'd never expect to roll the dice and go, oh, I got a 3.5. You don't actually expect to get a 3.5, but the expected value, the rolling average would be 3.5. So you could use something like this if somebody asked you, if you rolled the dice 1,000 times and added up all your rolls, what would you expect it to add up to? You can figure out, well, each roll has an expected value of 3.5, and there's 1,000 rolls. So I'd expect this sum to be 3,500. Just calculate the expected value and then multiply that by the number of rolls. Okay, so we're going to use this summation to figure out what is the expected value of the number of customers in our system. So when we get to a Q, an MM1Q, we want to know what is the expected number of customers in front of us. Well, whatever the probability of the Q being empty, multiply that by 0. The probability that there's 1 in our system, multiply that by 1. The probability that there's 2 in our system, multiply that by 2. And do this until we've run out of possibilities, and unfortunately it goes off to infinity. There is a possibility we have 100 customers in a system, and 1,000 and 1,000,000, so it's got to go off to infinity. So we take the value number in our system times the probability that we have that many in our system. Well, we know from before, the number in our system is I. The probability of being in that state, the percentage of time we were in that state, is captured by this. So since P0 is a constant, multiplying every term, we can move that outside the summation. We recall another power series from Calculus 2, that the sum from I equals 0 to infinity of I times x to the I minus 1 is equal to 1 over 1 minus x squared. This is true for all x between 0 and 1 again. It's actually true if you go down to -1 to +1. but since rho and mu are positive in queuing theory, we'll just state this to be true. So the expected value, we factored out the P0 is the summation of I. I'm now using rho instead of x. X from calculus, rho from queuing theory. Rho is a number between 0 and 1, so we're okay. And instead of having I times rho to the I factored out one rho because I wanted to fit it to this I times x to the I minus 1. So I factored one out, one rho. And I'm going to move that one outside of the summation sign too. So now what I've really done, I've just rewritten this as 1 minus rho, which is the probability that we are idle, probability we're in state 0. I factored out one rho so I can get the I minus 1 in the exponent. And I have the same summation. And we now know from calculus 2 that this summation can be rewritten as this. So we get rid of the infinite series. So the expected number in the system is 1 minus rho times rho divided by 1 minus rho squared. And then this 1 minus rho and this exponent of 2 we can get rid of. And we find it's rho over 1 minus rho. And then substituting lambda over mu, which is what rho is equal to, can tell us the number of customers in an MM1Q when we arrive to an MM1Q. Okay. So if you recognize from calculus 2 this summation equals this, we basically took this probability, this infinite series, which tells us the expected number in our MM1Q, and turned it into a non-infinite series. So, in an MM1Q, for example, if lambda equals 2 per second, 2 are coming into the queue per second, and the server runs at a speed where if it was 100% utilized, it could serve up to 3 per second. So that's good news that the rate into the system is less than the rate out of the system, so the queue won't grow off to infinity in size. If you want to know how much time does it take you, when you arrive at this queue at a random time, how much time it takes you to get through the queue, you have to know how many customers do you expect to be in front of you. And if it's a first come, first served queue, you get put on the end of the queue. They all have to get served first, and then you have to get served. And once you are served, then you're out. You're out of the system. So the time in the system is how much time you spend waiting plus the service of yourself. So we said last class that 1 over mu, the reciprocal of mu, is the service time. So if the server can serve 3 customers per second, that means each customer, if you take the reciprocal, takes 1/3 of a second to be served. That's the service time. Service time is 1/3 of a second. Rate is 3 per second. Okay, so your service time would be the number of customers we expect to be in the system, which we know is lambda over mu divided by 1 minus lambda over mu. That's the number. This is the number of customers in the system in front of us. They each take 1 over mu to be served, and then we have to be served. That's an additional 1 over mu. So the service time for an MM1Q where lambda is 2 and mu is 3, the number of customers is 2/3 divided by 1/3, which is 2. It's 2 customers in front of us. They each take 1/3 of a second each, so 2 times 1/3 is 2/3. It takes 2/3 of a second just to get all the customers in front of us out of the queue. And then we come along, 1 for us, and we take 1/3 of a second. So 2 times 1/3 plus 1 times 1/3 is a full second. 2/3 of a second to get all the stuff in front of us through the queue, and then 1/3 of a second to get us through the queue, total of 1 full second to get through the queue. Okay, and then, we were just talking about analysis from the point of view of an MM1Q. So we set up our birth-death equations. We could figure out what the probability is of being in state 0. We know there's a certain percentage of time we're in state 0. And then get the relationship from 0 to 1. We could then figure out the probability we're in state 1. Once we know the probability we're in state 1, we can then figure out the rate at which we go from 1 to 2 must equal the rate at which we go from 2 back to 1. But if we had, for example, an MN3Q, we have to first define all our states. We're not going to go through the analysis of an MN3Q, but just kind of like get started talking about it. State 0 means the whole system is empty. State 1 means we have a customer in one server, but the other 2 servers are completely empty, and the queue is completely empty. State 2 is 2 servers are in use, well, maybe this one's in use, this one's in use, and this one's idle, and the entire queue is empty. State 3 is all 3 servers are in use, but the entire queue is empty. State 4, which is shown in this picture, all 3 servers are in use, and in addition to that, there's 1 customer in the queue. And then state 5, that being X here, and so on. So we can figure out, based on the arrival rate into the queue and the cumulative service rate of the 3 servers, we could figure out the percentage of time we are in state 0. Nobody's in our system. There's a certain percentage of time, no servers running, and they're all sitting idle. And then there's a certain percentage of time where at least one is idle. So we can figure out the probability we're in state 0 from the lambda and the cumulative mu's. Now we have to set up our birth-death equation. At what rate do we go from state 0 to state 1 to figure out the probability we're in state 1? Then with that, we can figure out the probability we go, the rate at which we go from 1 to 2 must equal the rate at which we go from 2 to 1. And so, the birth-death analysis might look something like this. For an MN3Q, So what we could do is we could go from, if we're in state 0, no servers running, we can't go to state -1. We can't service anybody, nobody's in service. But we do go, the rate at which we go from state 0 to state 1 is the percentage of time we're in state 0 times the rate at which arrivals show up. That's the rate we go from 0 to 1. When we're in state 1, there's a percentage of time we're in state 1. There is a rate at which we serve customers, because 1 is being served. So the percentage of time we're in state 1 times the rate mu is the rate at which we go from 1 back to 0. When we go to when we're in state 1, if a new customer arrives, they immediately go into one of the 2 idle servers, and we go to state 2. When we're in state 2, we have 2 processes that are, in the oven, that are, they're being served. So the rate at which we go from 2 to 1 is 2 times mu, not 1 times mu, because there's 2 processes being served, and whatever mu is for each of the servers, we now have 2 times that, the rate at which we go back to state 1. To go from state 2 to state 3 means 2 servers are in use and a 3rd customer arrived. So the percentage of time we're in state 2 times the rate at which we go up to the next highest state, which is lambda, that's the rate at which we go from state 2 to state 3. The rate at which we go from state 3 back to state 2 is the percentage of time we're in state 3, and one of our 3 customers who are being served, any one of them completes, we would go then back to state 2. So that would be 3 times mu. And then because there's only 3 servers, now the queue starts building. Every state higher than that, the rate at which we go up 1 is lambda, and the rate at which we come down is 3 mu. And any new customer, if you're in state 4 and you go to state 5, the new customer gets put in the queue. So setting up an analysis like this, unfortunately there's no summation coming out of Calculus 2 that handles the MN3 case. But we could just punch this into an Excel spreadsheet and get all the probabilities for every state. Now we have to look at, for each of the states, how long does it take us to get through the queue? So for example, if we were in state 2, there's nobody here and there's nobody here. If we were in state 0, 1, or 2, and we arrive at the queue, how much time would we spend in the queue? None, right, good. We wouldn't spend any time in the queue because there's a server waiting for us. We go straight into service, and then whatever the speed is, that's the speed at which, that's the amount of time we would spend in the system. It's when we are in stage 3 or higher, do we queue? And then if we queue, then we have to calculate how much time does it take to get through the queue, and then how much time does it take to serve. So it's all doable, and we could cover that. We could probably spend the whole night talking about not MM1s, but any number higher than 1 analysis like that. So I just wanted to kind of like, maybe we'll whet our appetite on when there's more than one server, just to know it's doable. If, in case anyone was interested, I mean, that pretty much, that's the end of our lecture. If anyone has any questions, if anyone doesn't have any questions, then let me open up an Excel spreadsheet that just in case from your calculus days, if you don't have any background in calculus, this sum would equal this. We can just test it out. We can code up, we can sum from 0 to infinity in an Excel spreadsheet, but we won't go down to infinity. We'll go down to about 30, and we'll realize these numbers will go, some fraction raised to the 30 will be very, very close to 0. So after about 30, we get a very good estimate. So I'll just build a column in Excel from, let's say, 1 to 30, and then a column next to it. What does some variable x, which is between 0 and 1, raised to the I, what does that add up to? And then we'll sum them all. And then using the same x, we'll figure out what 1 minus 1 over that same x is and see if they match. So in this case, we have a lambda, we have a mu, and we have a rho, which is lambda divided by mu. And then our rho to the I, is going to be, so we have a column for I and we have a column for rho raised to the I, whatever I is. And then just add them up. Theoretically, I'm going off to infinity, but as you can see, once we get up to around 30, so I'm using a row of 1/3. Lambda is 1, rho is 3. Once we get up to around 130, this field is 4.8 times 10 to the minus 15. So it's very, very close to 0. After 30, they're really, really close to 0. So when Excel gives us an estimate, so the sum of all of these terms, the sum of the first 30 terms. So really what I'm doing in Excel is I'm saying from I equals 0 to 30, not to infinity, add up x raised to the I, and I'm using, we could use many variables, many values for x that are between 0 and 1. And just see what it compares to, 1 divided by 1 minus that same x. So if we look at this function, this is 1 divided by 1, 1 minus the same x. And in both cases, they came out to the sums came out to 1.5. If we used a lambda of 2, which would make, if lambda is 2, rho is 3, then mu is 2/3. And we use the same thing. For 2/3, it would sum up to 2.99999, and the actual fraction would be 3. So those are, like I said, we're supposed to sum off not to 30 and stop. We're supposed to sum off to infinity. But we're adding, at this point, we're adding such really small numbers, I kind of ignore it. So the 2.999 and the 3, I'm saying are equal to each other. The other summation we looked at, again, if you're not familiar with these summations from calculus, this one, this summation right here. This is just a fact of mathematics, that the sum from 0 to infinity of I times x to the I minus 1. This sum, instead of calculating it off to infinity, is always equal to this for values of x between 0 and 1. I divided by 1, I minus 1 squared. And basically did the same thing in this spreadsheet. We have a lambda, a rho, and then mu is equal to lambda divided by rho. And then we just summed up. Actually, the first term in the summation shouldn't really exist, because when I is 0, I minus 1 is actually negative 1. But we're multiplying that result by the value of I, which would be 0. So it's 0 out the term. So we could even, this is true for I equals 0 to infinity or 1 to infinity, because the term when I is 0 is 0 anyway. So for example, these terms are basically, so these are the i's in this column, and then this column is I times the number x, between some number between 0 and 1, raised to the I minus 1. And we write that in that box, and then do that for every, and then copy that formula all the way down to 30. And so, for example, when lambda is 2 and rho, mu is 3, and the value of rho is 2/3, this summation adds up to 9. And then the actual formula itself, 1 divided by 1 minus rho squared, is also equal to the same value, 9. So like I say, this is 8.99949 because I went to 30 and stopped instead of going off to infinity. If I went off to infinity, this would become 9. And we could try many values as long as we stay between 0 and 1. So with using x of 1/3, they both equal 2 1/4. So just whatever number you put in, these two would still keep coming out the same. So basically, all we're saying is maybe you know this from calculus, maybe you don't know this from calculus, but this summation equals that fraction. The reason we like to use these is because it's a pain. You have to write a program or use a really big Excel spreadsheet to calculate this. But if you happen to have this identity that this summation always equals this, then we can just come up with a very simple formula. We don't have to count off to infinity. Okay, so any questions on this topic? So what we're going to do now going forward is we're going to take, anytime we encounter an MM1 cube, we know exactly how many customers are in it at any random point in time. So if we show up at a random point in time, we know this many customers are in front of us. Okay. And if we know that many customers are in front of us, then we know we have to service all those. If it's a first come, first served queue, we have to service all those customers, and then we have to service ourselves, and then we're done.